Hey everybody, it's Friday, March 26th. As you can see here in the aim today, our goal for today's video is all about how we can describe the motion of a spring block oscillator. Now, yesterday we spent the majority of the video talking about oscillatory motion in general, what an oscillation is, what are characteristics of periodic motion that's experienced by an object that's oscillating. We talked about things like the period, the frequency, the amplitude, and sort of saw how we can use graphs to describe the motion and really use the graphs to figure out what those characteristics of the motion are, like period, frequency, amplitude, et cetera, et cetera. For today, our goal is to really step up our level of analysis and really bring some math into it by talking about the motion in a little more detail. Now, as you can see here, we are also talking about the motion of a particular kind of oscillator called a spring block oscillator. Before we get to that, though, I just want to take a look at one more question. This question I did want to include in yesterday's video, but because it was getting a little long, I decided to save it for today. And so let's take a look at that first before we get into the spring block oscillator. This question is in the simple harmonic motion packet. It's on page 31, number 4. And it says here, figure P11.4 shows a plot of the position as a function of time for a particle undergoing simple harmonic motion. Identify the following points on this graph. Where is the speed the largest? B, where is the velocity positive with its magnitude being largest? C, where is the magnitude of the acceleration largest? And D, where is the force on the particle 0? I want you to try this on your own, but we're going to do it in parts. Because A and B are really, really similar, I want you to start there. Notice here where it says, identify the following points, you are literally to pick the points on the graph, list them, 1, 2, 3, 4, 5, 6, 7, depending on whether they apply to that question being asked in each part or not. So what I'd like you to do right now is take a minute to pause this video here and answer A and B. Not only do I want you to come up with an answer, but I'd like you to think about the reason why that's the answer. Because obviously that's going to be really important when it comes to answering these kind of questions in the future. So take a second to pause this video and answer A and B. And when you hit play, we'll go over it. So A is asking where is the speed the largest, and B is asking where is the velocity positive with its magnitude being the largest. And I think, as we mentioned yesterday, hopefully you've realized that a lot of old concepts apply to the way we analyze the motion for these objects that are oscillating. They're telling you here that this figure is showing you a plot of the position versus time. This is a position versus time graph. At the end of the day, all of the concepts we learned about graphing apply to this kind of question. And so because this is a position versus time graph, we can use the concept of the slope to make determinations about the velocity. That's the idea. And so here, we can look at the individual slopes of the tangent line and make a determination about when it's the largest. I think what you should hopefully realize here is that the slope is the steepest when x equals 0. So when this thing crosses the x-axis, the slope of the tangent line is larger, is largest. Notice here, the velocity is at 0, and then it gets bigger, 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 until here, when the tangent line begins to get smaller, 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 or I should say the slope of the tangent line gets smaller and smaller and smaller until it eventually comes down to 0. These points, which can be noted as the equilibrium position, are where the speed is the largest. So the speed is the largest at points 1, 4, and 6. Now, what I've seen in the past is that people usually leave 1 out and say, well, the speed isn't largest at 1 because at 1 it's not moving. X is 0. It's important to realize that when they tell you here that x is 0 at time t equals 0, that just means they are starting this graph from when the object is at the equilibrium position. The fact that the position is 0 or the time is 0 or that it's at the origin of the graph has nothing to do with it. The velocity or the speed is all about the slope of the tangent line. So the answer to A here is 1, 4, and 6. And if you look at question B, basically question B is asking you the same thing, but they're asking you about where the slope is positive. And if you look at the slope of the tangent line for 1, the slope of the tangent line is positive. If you look at it for 4, it's negative. So that's not the answer to B. And of course, if you look at it for 6, then it's positive again. And so the answer to B is 1 and 6. And so the explanations are just going to look a little something like this, or at least the answers. The speed is the largest at the object's equilibrium position, which is where the slope of the tangent line is largest. And the velocity is positive and largest at the equilibrium position, and when the slope of the tangent line is positive and largest. And so that would be at points 1 and 6. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from what you wrote before. And when you hit play, we'll take a look at the next part. That brings us to part C. Part C of this question asks, where is the magnitude of the acceleration the largest? Now, we did talk about this briefly yesterday, but take a second to pause this video here and try to answer part C, come up with an answer, come up with an explanation, and when you hit play, we'll go over it. Now, part C is asking about where the magnitude of the acceleration is the largest. Again, this is a position versus time graph. And so what you need to be thinking is that the slope of the tangent line is the velocity. Now, the key detail here is this question is not asking about the velocity. It's asking about the acceleration. The main point here, though, is that the acceleration is largest when the rate of change of the velocity is largest. And what we talked about yesterday was that at the turning points, the rate of change of the velocity is largest. And that's when the velocity is changing its sign, in the case of point 2 here, from positive to negative. In the case of point 5, from negative to positive. And in the case of point 7, from positive to negative. When the objects are at the location where their displacement is the largest from the equilibrium position, or in other words, the amplitudes, that's when the acceleration is largest. And so the answer here to C is 2, 5, and 7. And so for C, we can say the magnitude of the acceleration is largest at the amplitude, which is when the slope of the tangent line changes the most. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, we'll move on. That brings us to part D. Part D here is asking where the force on the particle is 0. Now, this question is a little weird. You really need to think your way through it, but give it a shot. Take a second to pause this video here and try to answer this question, come up with an answer, come up with an explanation. And when you hit play, we'll go over it. So for D, they're asking you where the force on the particle is 0. Now, ultimately, this is going to come down to you recognizing that the slope of the tangent line has a very brief instant where it is constant. If you really look at this thing where the acceleration is largest, which is at point 2, and you follow the slope of the tangent line along, you'll recognize that right here, for a very brief instant, the line is straight. That means for a very brief instant of time, literally just an instant, the object is not accelerating. The line is not curved. It is momentarily perfectly straight. And so the idea here is that for a brief instant at the equilibrium positions, 1, 4, and 6, the object is not accelerating. And if the object is not accelerating, well, because F net equals ma, that means there is no net force on the particle. Now, to be clear, we are going to talk about this in great detail in the future. Really get into the idea of why the force is 0 there. It makes a lot of sense. But the point is, the object here is being sped up from 2 to 4 and then slowed down from 4 to 5. And so the point here is, as the object changes from having a force exerted in the direction of its motion to make it speed up, and then the force opposite the direction of its motion to slow down, there's a brief instant where that force momentarily goes to 0 in this case. Now notice that's not the case for gravity, because the force of gravity is always acting in the same direction there. But because the force is literally changing directions here as the object oscillates back and forth, it has a moment where it goes to 0. And so for our answer here, we can write for D, there is no net force acting on the object when there is no acceleration. There is no acceleration when the slope of the tangent line is constant. For a brief instant, at the equilibrium position, note the name equilibrium position, the object is not accelerating, meaning there's no net force. That makes the answer here points 1, 4, and 6. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, to summarize what we just said here, we can take a look at the notes on this slide. This stuff is very important to remember. You can write this down if you want. We did just basically write down a lot that's very similar to this, but the point is the velocity of an oscillator is always the largest when it moves through the equilibrium position, as that is the location where the position versus time graph has the largest slope, or really the slope of the tangent line is largest. The acceleration is largest at the amplitudes, as that is the location where the slope of the tangent line changes most. And that, of course, should make sense because acceleration is defined as the rate of change of velocity. And then lastly, the net force is 0 at the equilibrium position. That is an extremely important thing for you to know. I really do think it would be a smart idea to write this down, so I'll just say, take a second to pause this video here and write that down. And when you hit play, we'll move into the main portion of today's video. So in the last couple of days here, we have been throwing around the term simple harmonic motion, but we have not fully defined what it is yet. I want to do that now because now we are ready to transition into the next phase of understanding oscillatory motion. And so let's just say simple harmonic motion is defined as a special case of oscillatory motion, which we defined yesterday, where an object moves under the influence of a restoring force, which is proportional to the object's distance from its equilibrium position. There's a lot there, but there's a lot in here which also should make you remember some things we said either previously in yesterday's video or previously this year. So notice the term oscillatory motion refers to an object moving back and forth. And basically, we're saying that it's moving under the influence of a restoring force because as it moves back and forth, like let's just say this is the equilibrium position where x equals 0, when the object is to the right of the equilibrium position, there's a force acting on it to the left to try to bring it back to the equilibrium position. And when it's on the left of the equilibrium position line here, the force is acting on it to the right, trying to bring it back to the equilibrium position. That's the idea. The main thing in this that should really be jogging your memory is that that force is proportional to the object's distance from the equilibrium position. Now, I'm going to take this off the screen in a second here, so take a minute to pause this video and write this down. And as you are writing it, I want you to think about where you've seen this concept of a force being proportional to the distance from the equilibrium position. And when you hit play, we'll talk about it. We've talked about forces being proportional to the equilibrium position before. For a spring, this is very important to realize. We are saying that when an object is attached to a spring, it is experiencing simple harmonic motion because the force exerted by the spring is always trying to get the object back to the equilibrium position. Now, notice here, this means when we pull on the spring to the right, like if we just literally stretch the spring to the right, well, according to Newton's third law, if you pull on the spring to the right, then the spring pulls on you to the left. Of course, Newton's third law is governing this interaction, so when that force is smaller, the force the spring exerts is smaller, and when that force gets bigger, of course, it's because the applied force is bigger. This part is very important and informs the answer to part D for the last question. When it's at the equilibrium position, the force is 0 because the spring force equation says the force is directly proportional to the distance from the equilibrium position. So when the distance from the equilibrium position is 0, or in other words, when it's at equilibrium, the force is 0. That's a very important idea. The spring force here is the restoring force for these very special types of systems experiencing simple harmonic motion because it's always trying to get the object back to the equilibrium position, and it's bigger when the stretch is bigger, and it's smaller when the stretch is smaller, and they are directly proportional. The force is directly proportional to the distance from the equilibrium position. Now, this kind of oscillator experiencing simple harmonic motion is the kind of oscillator that was alluded to in today's aim. It is called a spring block oscillator, or SBO for short. You will see me in writing refer to this as an SBO. A spring block oscillator is a simple system consisting of a spring and a block moving without friction. Since the only force acting on the system is the restoring force exerted by the spring, this is an example of simple harmonic motion, particularly, of course, because that spring force exerted by the spring is directly proportional to the displacement from the equilibrium position. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, the fact that a spring is the restoring force for a simple harmonic oscillator here, or this spring block oscillator, is really important, because now we are ready to step up our level of analysis of this kind of problem to include ideas about forces. If you remember, when we started this, I was saying this unit really is a synthesis of every single thing that we've talked about this year. Now we're moving into the forces phase. We talked about position versus time graphs and how we can use all those ideas about motion to make graphs and whatever. Now we're ready to talk about forces. The fact that the force here is just an ordinary spring force means we can have a pretty easy time analyzing this. But before we actually get into the forces analysis, there is one more super important point that I want to make. And that super important point that I want to make here, I think, is best shown by this video. This video is just a video I found on YouTube. I really do think it is a very good representation of the concept we're going to get at here. What this video shows is an object experiencing simple harmonic motion. Look at it. It's going up and down and up and down. But when they show you the side view, you see that this object is actually moving in a circle. I kind of showed you something like this yesterday. But I think the key point behind this video is they really show you the full-on side view. It's basically impossible to see that the object is moving in the circle until you turn it. And that's a really important idea, that we can think of simple harmonic motion as being like a projection of circular motion. That's a very important idea because it informs all of the math we do. It's a super pain to do this kind of work with forces because the force is always changing. But if you notice, if we literally project the shadow onto the wall, we see that an object in uniform circular motion, at least in the vertical direction, it's also true in the horizontal direction, in each direction it's experiencing simple harmonic motion, we can at the very least say uniform circular motion has a lot of similarities to simple harmonic motion. And as such, we can actually use a lot of mathematical analysis for simple harmonic motion to be able to derive the equations from uniform circular motion. Effectively, what we're saying is this is really similar to uniform circular motion. We're going to go ahead and use uniform circular motion equations to derive our equations for simple harmonic motion. And that's what we're going to do here today. All right, so the first thing I think you should be doing when we go through this derivation is always referencing this diagram. So I know there's a lot. I want you to take a second to pause this video here and draw this diagram. When you hit play, we'll talk about it in great detail and then do the derivation we want to do for today. The first thing that I think you should notice about this diagram is what we are trying to do is we are trying to compare the motion of an object experiencing simple harmonic motion, so just moving back and forth, to an object moving in a circle. Notice on top of this circle, I've drawn an XY axis set here, Cartesian coordinates, because I think it's very important to realize these objects are experiencing simple harmonic motion only in each direction. If we just look at the Y coordinate as the object moves around the circle, the object gets farther and farther and farther from each axis until it gets here, and then it gets closer and closer and closer. So whichever way you look at it, whether you choose to slice it up like this, and this, is up to you, whether you're considering the simple harmonic motion in the X direction or in the Y direction. But the point is, in each direction, the object is starting at some distance farthest from the equilibrium position. On the Y-axis, we'll say that that's here, where this is going to be our equilibrium position. I'll label it with a 0. Or on the X-axis, here is the farthest it gets from the equilibrium position. And as it moves around the circle, its distance from the equilibrium position is changing. If we're talking about where X equals 0, so along the X-axis, notice here, this distance is the farthest it's ever going to get, so we'll call that the amplitude. And then as it goes here, around the circle, it gets closer and closer and closer to the place where X equals 0. Notice, as it's doing that, on the Y-axis, it's getting further and further and further away from the equilibrium position until it gets here, where it's farthest from Y equals 0. Then notice as it goes back, it's going to get closer and closer and closer to Y equals 0. Additionally, what we should reference here, now that we've talked about the circular diagram, is what the simple spring block oscillator diagram is showing. Notice when we're saying when X equals 0, the spring force equals 0. When x is greater than 0, notice that's because this displacement here is to the right, and so we're considering that to be a positive x. The spring force is negative. They're opposite. When the block goes to the right of the equilibrium position, the spring force is pulling back left because it tries to restore the object to its equilibrium position. Notice here, when it's to the left of the equilibrium line here, so this delta x is negative, if you want to refer to it like that, then the spring force is positive because it's trying to restore it back to the equilibrium position. Now, as I already wrote down in this video, we always use the equation Fs equals Kx. But if you look at it in the reference table, it shows it like this. They say the absolute value of the spring force is equal to K times the absolute value of the position vector. And the reason why that's true, the reason why they include the absolute value symbols on the distance from the equilibrium position and the spring force is because in most college physics textbooks, they actually print it like this. Now, the reason most college physics textbooks print it like this is because the force is always opposite the direction of the displacement. The reason why, as I mentioned, is because it's always trying to pull the object back towards its equilibrium position. So when it's displaced to the right, the equilibrium position is to the left of where the block is, so the force acts to the left. And when it's to the left of the equilibrium position obviously then is to the right of where the object is, and so the force pulls to the right. It's very important to realize that up to this point, we never cared about the direction of the spring force, whether it was opposite to the displacement or whatever. But for these kind of problems, it's very, very, very important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So now we are going to use these ideas to come up with an equation. Now, of course, a reasonable question for us to ask would be, well, what should we come up with an equation for? What we should come up with an equation for is something at the very least that is unique to periodic or oscillatory motion, or in other words, simple harmonic motion. Now, obviously, things like velocity and acceleration and, forces and all that stuff comes into play. It's not unique to simple harmonic motion. What is unique to simple harmonic motion are the characteristics we talked about yesterday: amplitude, period, and frequency. Now, deriving an equation for the amplitude doesn't actually make sense. If you remember in yesterday's video, I showed a very brief clip where I had keys hanging from a spring, and I pulled on the keys. I gave them a little displacement from the equilibrium position, and then it started to oscillate. What the important idea here is that you, the person who's setting the system into oscillation, you determine the amplitude. If you pull on the spring a little bit, only a small distance, it will oscillate with a small distance. If you pull on it a lot, it'll oscillate a lot and travel a large distance. Since the amplitude is set by the person who sets the system into simple harmonic motion, it doesn't make any sense to derive an equation for that, because ultimately you determine that. What it does make sense to derive an equation for, I think, is the period. And so that's what we're going to do here. Notice I've included these diagrams again on this slide because I think it's an important thing to reference. Now, notice in these two diagrams, in the spring block diagram, I've shown the object at the equilibrium position. And in the circular motion diagram, the object is not at the equilibrium position. What I want to do for this mathematical analysis is I want to imagine the object at the equilibrium position. So instead of having the object here, let's just say the spring extended and the block was here. And so it's at its amplitude. This is just for the purposes of this analysis. Obviously, the amplitude is a really interesting part of simple harmonic motion, and so that's why we're going to use that as our reference point for our derivation. For the purposes of the circular motion concepts that we're going to employ, instead of imagining the object here as it moves around the circle, we're going to imagine the object here. And just for our purposes for now, we are going to consider only the oscillation of the x-coordinate of this object. So as this object moves around the circle, its x-coordinate really is just going back and forth and back and forth. And here, the object is at its maximum negative displacement from the equilibrium position, which is there. And so this distance is actually x equals negative a, but the magnitude of the displacement, of course, is just the amplitude. And so I want you to keep that in mind as we're going forward. We'll start by talking about the spring block oscillator. In terms of a forces analysis here, there's not really a whole lot that we can possibly say. As we just saw, a relevant equation for the spring is that the spring force equals negative kx. That's just a fact. That is an equation that relates the spring force to the displacement. They are negative because of the nature of the restoring force, but either way, the spring force is always opposite the direction of the displacement. It's defined by this equation. The only other equation in terms of forces that we can possibly use here is whatever net force is acting on the block, well, that's got to be equal to m times a according to Newton's second law. And so basically the only thing we can do here is we can just like very quickly go back to this definition and say the only force acting on the system is the restoring force. That's the definition for the spring block oscillator here. It's the defining quality. And so what we can say then is if the only force acting is the spring force, then we can write an equation that looks like this. F net equals Fs. And so what can we do? Well, the equation for F net is ma, and the equation for the spring force is negative kx. But of course, because we said we were going to consider the object when it was at its amplitude, we can say when x equals a, then we can write ka, k times the amplitude, equals m times a. And that really is the governing equation in terms of the spring force that we can use for this object. Now, I know some of you looking at this math here are probably thinking, wait a second, he just dropped the negative sign. He forgot the negative sign. I didn't. X is a vector. A for amplitude is a scalar. And so when we are using the amplitude in this equation, because it is just a scalar, it doesn't really matter. The point is, if we were to solve this for the acceleration, we would have Ka over m. And a is just a scalar. It's just the magnitude of the displacement. And so here, this equation is just going to give you the magnitudes of these quantities. And so I'm going to write here in parentheses, magnitudes. You're going to be able to figure out the direction of the acceleration by figuring out the direction of the force. It's important to realize, though, since that's continuously changing, we're just going to want to sub the magnitude of the displacement or the amplitude in there and just not go too nuts about the direction. So that's the first part. The second part is going to be how we can describe this object moving in a circle in terms of uniform circular motion. Again, the reason why we're doing this is because an object experiencing uniform circular motion looks really similar to an object experiencing simple harmonic motion. So of course, the first thing we can say is Fc equals mv squared over r, right? Centripetal force equals mv squared over r. And we can also say, well, F net does equal ma, after all. That's a fact, right? And so for the object moving in uniform circular motion in exactly the same way that here the net force was equal to the spring force, here the net force is equal to the centripetal force. Pretty good. And so we can say ma is equal to mv squared over r. But of course, just like we did over here, when we said the object was at its amplitude, that's when its x position is largest, the largest magnitude from the equilibrium position, and that's where we're considering the object. And so what we're going to do here is we're going to say we are considering the motion of this thing specifically when the object is at its amplitude. And so we're just going to rewrite that equation by saying ma is equal to mv squared over a, the amplitude. And now we should be thinking, well, if we're doing this analysis, there's not really a whole lot that we have left to say. It's important to recognize here that what we are trying to do is come up with an equation for the period. Now, of course, it's very difficult to come up with an equation for the period using the spring block oscillator equations alone. And so that's why we work in the uniform circular motion equation, because number one, there are a lot of similarities between uniform circular motion and simple harmonic motion, but also because we've talked about period in the context of uniform circular motion before. Let's flip to the next slide. You may want to take a second to pause this video here and make sure you have all this written down before we move on. So what you should recognize at this point is from the spring block oscillator equation, what we've obtained is Ka equals ma. And what we've obtained from our analysis of uniform circular motion is that mv squared over a is equal to ma. Now, of course, there's not a whole lot to do with these until we recognize that if this is equal to ma and this is equal to ma, then those have to be equal to each other. So we can write Ka equals mv squared over A. Now the big question is, how do we work in period into this equation? And the way we work period into this equation is pretty simple. K is the spring constant, it's just a number. A, the amplitude, is the maximum displacement from the equilibrium position. You determine that when you are doing this kind of experiment with these springs. You pull it back a certain amount, and that's what the amplitude is. Of course, the mass is just a number, and then we have amplitude again. We work it in through the velocity. Remember, from uniform circular motion, when an object is moving around a circle with a velocity and it completes one cycle, we say here that one cycle occurs when the object makes it around the circle once. The distance it travels is the circumference of the circle. And since the definition of period is it's the time taken to go around the circle once, we can put t in here for the period. Now, of course, I can write 2 pi r for the period, 2 pi r for the circumference, but because we are treating the radius of the circle as the amplitude, I'm going to write 2 pi a over the period for the circumference over period equation. Now, of course, doing this substitution with a fraction is going to be a little annoying. And so what I'm going to do here is I'm going to recognize the frequency as the inverse of the period. And I'm going to say that this equation can be written as 2 pi f times a. It's also important to realize, and I'm just going to make this as a side note, yesterday we said omega is equal to 2 pi f. It's just like the rotational version of regular old frequency. And so we can actually also write this as omega a. But here, what should be recognized is the velocity in this equation can be written in terms of the frequency, which will ultimately allow us to write an equation for period. And so what we're going to say here is Ka equals mv squared, where v is equal to 2 pi f a. So we square that and then divide it by a, the amplitude. Now, notice we're going to have to square this whole term. What I'm going to do here is I'm going to bring this a to the other side. So I have Ka squared, and that's going to be equal to m times 2 squared, which is 4, pi squared, which is pi squared, f squared, which is f squared, and a squared, which is a squared. Now, the first thing that we should notice, and this is going to come up quite a bit over the course of the next couple days, the amplitude cancels. The amplitude does not affect the period, does not affect the frequency. Pretty interesting. And so what we get here when we solve this for f squared is pretty straightforward. We just take the m, the 4, and the pi squared, and we divide it to the other side. So we get k, and I'm just going to rearrange to write all the constants in front, k over 4 pi squared m. And so to get our equation for the frequency here, I'm just going to write f is the square root of k over 4 pi squared m. Now, obviously, that equation is a little disgusting. We could leave it like that, but I want to reorganize it. And so we'll say here, well, we could separate out first, right? Because the product of the square roots is equal to the square roots of the products, right? And so in other words, if I have AB over CD all under the radical, I can write that's root A times root B over root C times root D. Everything under a radical can be separated. So I can write this as root 1 over 4 pi squared times root K over M. And so notice here that this term I can easily handle. The square root of 1 is 1. The square root of 4 is 2. And the square root of pi squared is pi. And now I have my equation in its final form. The frequency is 1 over 2 pi times k over m. And what I think is really interesting here is now that I have an equation for the frequency, I can very easily come up with my equation for the period. Because the period is the inverse of the frequency, meaning all I have to do with a frequency is flip it to get the period, all I have to do with all the terms in this equation is flip them. If I take the inverse of 1 over 2 pi, I get 2 pi. If I take the inverse of the square root of k over m, I get m over k. And that's my equation for the period. The point here was that by combining our forces analysis from an object moving on a spring and uniform circular motion, we are able to come up with an equation for the period, which usually was only useful for circular motion stuff, we can come up with an equation for the period in terms of things like the mass of the block on the spring and the spring constant. Now, obviously, doing this was kind of like an educated guess. Of course, we only know that this works because basically what we do is we take an object with a certain mass, put it on an end of a spring with a known spring constant, and we set it oscillating. And we use a stopwatch to measure the period. And if the number for the period is the same as what the equation predicts, then we know this equation is right. And ultimately, that's how this ends up working out. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so just very quickly now, before we jump into some problems, let's just formally introduce these equations. For the frequency of a spring block oscillator, we can say the equation here is a frequency equals 1 over 2 pi times the square root of k over m. Now, I know it seems kind of weird that I was saying this whole time, we're deriving an equation for the period, we're deriving an equation for the period, and then I ended up showing the bulk of the derivation using the frequency. There's a reason for that. I'll get to that in a minute. In this equation, of course, m is the mass measured in kilograms, k is the spring constant measured in units of newtons per meter, and the frequency is measured in hertz. Now, I think it is important to notice, I want to say two things about this equation real fast. Notice what this equation tells us here is that the frequency is directly proportional to the square root of k, and the frequency is inversely proportional to the square root of the mass. Now, that makes a lot of sense. Frequency is the number of cycles per second. If the spring constant is larger, that means the spring is stiffer. And a stiffer spring is going to whip the object back and forth more times per second, which makes the frequency increase. Notice the frequency is inversely proportional to the square root of the mass. That means if an object has a larger mass, the frequency will be less, or there'll be less cycles per second. Of course, that makes sense too. If an object has more mass, has more inertia. And so it's going to be harder to move back and forth. And so that's why the frequency would be less. The other thing to point out here is yesterday, in our work on the slides and in the reference table, we said omega is equal to 2 pi f. And notice when we take this equation, frequency equals 1 over 2 pi times root k over m, we see here that if we move that 2 pi to the other side, we get 2 pi f equals k over m. And so that means omega can also be written as the square root of k over m, which is also a nice, interesting little relationship. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And just very quickly here, let's just jump through the period equation here. Notice the symbol is uppercase T. As you'll see in a second, in the reference table, they actually put a subscript S on there. And so I think it's actually a smart idea maybe to go back and put a subscript S on here too, just to show that this is for a spring, where of course the equation is just the equation for the frequency flipped. So we have 2 pi times the square root of m over k, where m is the mass measured in kilograms, k is the spring constant, and of course t is the period measured in seconds. So that means this unit here should be written as seconds. And let's just show very quickly, the period of a spring is directly proportional to the square root of the mass. That makes sense. More mass, more inertia. It's going to take more time to go back and forth. And of course, the period is inversely proportional to the spring constant, or the square root of the spring constant. So that means a stiffer spring would make the period lower, because of course the stiffer spring would whip the object back and forth faster and make it take less time per cycle. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, and just lastly here very quickly about these equations, since the period is the inverse of the frequency and vice versa, all you have to do is take the inverse of each individual term in the period equation to get the frequency equation. The reason why I bring that up is because the period of the spring equation is the only equation in the reference table for the spring. The frequency one is not in there. That's actually why I ended up showing the derivation in terms of the frequency the whole time, because I want you to remember that you can get that either by deriving it or just from the equation for the reference table. But I want that to stick in your brain. The frequency equation is not in the reference table. If you want the frequency equation, you literally just flip everything over in this equation in the reference table. You flip over the 2 pi and you flip over what's under the radical, and boom, you have your frequency equation. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so very quickly before we go here, let's take a look at a couple of examples. First example here is in the simple harmonic motion packet. It's on page 31, number 13. This problem here says, consider the mass on the spring in figure 11.6. Now, obviously, you can't see this figure in this particular question, so just pretend it's a spring. It looks like this. It's a block attached to the end of the spring, and this surface is frictionless. It says here, if the spring constant is 30 newtons per meter and the mass is 2.5 kilograms, what is the period? Okay, so it says here, K, the spring constant, is 30 newtons per meter. And they tell us here that the mass is 2.5 kilograms. And they've asked us for the period. And I'm going to put the subscript S on it because that's what it shows in the reference table. The period of a spring is 2 pi m over k, or I should say 2 pi times the square root of m over k. And I think it's important to realize whenever you're trying to think about what this equation looks like, or if you confuse this with the frequency one, is it m over k? Is it k over m? Which one is it? I can't remember. It's always important to remember it really makes sense for the period equation that the mass is in the numerator, because an object with a larger mass has more inertia, and so it's going to take more time for it to go back and forth. I think that's a good way to remember it. And so this, I think, as you'll realize, is just a pretty straightforward plug-in. You take the mass, 2.5 kilograms, you divide it by the spring constant, 30 newtons per meter. You make sure you have it underneath a radical. You multiply by 2 pi, and when you do that math, you get the period is 1.8 seconds. And that's it. Pretty straightforward. Now, just for fun, we can also say, well, what's the frequency here? And as you'll see, if we use the frequency equation, 1 over 2 pi times square root of k over m, if we plug in those numbers here, the frequency is 1 over 2 pi times the square root of 30 newtons per meter over 2.5 kilograms. Then we get a frequency of 0.56 hertz. And notice, if we take the frequency and recognize that that's 1 over the period, if we just did 1 over 1.8 seconds, sure enough, we would get 0.56 hertz. It's very important to remember that all of these things are connected. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at one more example before we go. All right, I think this stuff is really important, especially for the AP test, so I just really want to make sure that you can do this stuff on your own. Here's an example of a problem. It says the period of oscillation for a mass on a spring system is 0.22 seconds. And it says if the mass is 3.5 kilograms, what is the spring constant of the spring? So really all I want you to do here to submit for today is to answer this question. As you can see, it's on the Simple Harmonic Motion Packet, page 31, number 12. Show the work, solve this thing out. And when you're done, submit it through Google Classroom. Now, because it is Friday and it is the day before a break, I am not going to show the solution to this problem until the video on Monday after the break. So technically, that's when it's due. I think this will probably be pretty easy to forget about, though. So if I were you, I would just get this over with, hand it in, bada boom, bada bing. All right, everybody, have a good break. I'll see y'all when we come back. Take care.